Hello everyone, good evening.
Good evening.
Okay, so I hope like everyone joined the meeting. So today we have Akash Singh Chia. So he's our like ISA India trainer. So he's going to provide you the insights on communication protocol. So I think you are already aware about the topics. So Akash, you can start the session. Okay, thank you. Thank you everyone. Over to you, Akash.
Okay. Thank you, sir. So, am I audible? Everyone, am I audible?
Yes, sir, you are audible.
Okay. Is my screen visible to all?
Yes.
All right. Okay. Let's start. Okay. So, first of all, good evening, everyone. I hope you all are doing well today and excited for today's session, right? And first of all, thank you so much for joining this webinar on communication protocol in electric vehicles, CAN, LIN, and BMS. Okay. So before we start, I want to ask you all a simple questions like how many of you have heard about CAN protocol before today? How many of you have heard about CAN protocol? Can anyone tell me? You can open your mic or you can just type on the chat box. Okay. Just a second. Just a second. All right. Right. I can see the messages. I can see the messages. All right. Okay. So as we all know that actually behind every smart electric vehicle, there is a complete communication network which works continuously, just like the nervous system in our human body, right? And like different electronic control units like sensors, battery packs, motors, chargers, they all talk with each other, like how they are talking with each other. They just need a communication system like nervous system. That's how we communicate with all the systems in a EV. Okay, so and this communication happens like through protocols like CAN, LIN, and some battery management system, and many other ECUs are present in this, right? So today we are going to understand about all these things, and uh, before moving ahead, can you just let me know in the chat, are you from the mechanical or electrical or CS background? Can you just let me know so I will just get an idea about maybe how much you know about the systems and about the electronic components which are used in the electric vehicles? You can just type on the chat box. Great. Okay. Maybe some of you know, maybe some of you don't know about these systems in detail about the communication protocols, but don't worry. If you are completely new to this topic, don't worry. I will explain everything from the basics to advanced concepts in a very simple and practical way today. Okay, and don't worry, we are not going too deep into the complicated coding in this. Okay, so today we will just decode the hidden languages through which EV communicates. Okay, so but one thing I ensure you guys today, like by the end of this today's webinar, you must get a clear understanding about how these systems are working inside an electric vehicle. Okay, and why these protocols are considered the backbone of our modern automotive technology. Okay, so let's move forward. Here the first question arises, like why communication matters in the EV. Okay, so here you can see some few points, like it enables the coordination between multiple ECUs. ECUs means electrical control units. Okay, so like modern electric vehicles are not just mechanical systems, they are the data driven machines, right? So inside a EV, multiple systems like battery, motor, inverter, and many sensors are constantly exchanging information. For example, the BMS is our battery management system, which continuously monitors voltage, temperature, and always shows us the state of charge. Right. So this data must be shared with the motor controller and to decide how much power can we safely deliver to the wheels. Similarly, during the braking or the acceleration, real-time communication ensures like smooth coordination between the different systems, right? So if these communications is delayed or fails, it can directly affect vehicle performance, right? So all these systems, they are communicating with the help of some protocols like CAN. Okay, so protocols like CAN and LIN make this communication very fast and reliable, and organized, reducing it also reduced our like wirings in our vehicles. So if we say in the simple terms, communication in EV acts like a central nervous system. Okay, so that connects all the components and enabling intelligent operations in our EV. Okay, so let's understand what exactly the CAN bus is. Okay, so uh, I will decode this in a very simple way, so you must get an understanding about how, what exactly the CAN bus is. Okay, so think I will give some examples so you will get more better understanding. Okay, so just think like CAN bus is like a WhatsApp group chat. Okay, so imagine, just imagine a WhatsApp group where every person is an ECU, where everyone is an ECU in a WhatsApp group. Okay, and the group chat is our CAN bus network. Okay, so just imagine this. Okay, now see how it works. Okay, suppose when someone sends a message in a group, everyone can see it, right? Just like in CAN, messages are broadcasted to all the ECUs. As we know that in the modern EVs, there are 70 plus ECUs are present in the vehicles. Okay, so just like this, maybe 70 plus or 100 plus persons are present in the group or added in the group. So just like in CAN, messages are broadcasted to all the ECUs in an electric vehicle. Okay, so we are imagining about the WhatsApp group. Okay, but each person only reads like messages which is relevant to them in a WhatsApp group. Same here in the CAN system. Here each ECU filters the information and the messages which is only relevant to them. Okay, and how it works, like it uses some IDs or the identifiers. Sorry, ID or identifiers. Okay, so Sorry, my pen is not working here. Okay. So yes, I think someone mic is on. Okay. So in this same ECU filters messages using ID, like the identifiers. Okay. So suppose if two pupils are trying to send a message at the same time, same in the CAN system work, like the one will get the higher priority message. Okay. Or gets his message may get first sent. Okay. So other will wait that time, and the waiting process in this system, we call it as the arbitration. But we call it as arbitration. My pen is not working clearly. I don't know what happened with my pen. Okay. Yes, now it's clear. So, yes. So in this, maybe there are some high priority messages which get sent first, and the other person will wait that time. And that process, we called it as arbitration. We call it as arbitration in the CAN. Okay. So, like there is no central boss which is controlling the chat here. Only the CAN is a master, like the multi-master system here. And here, any ECU can send data. Okay. So CAN bus is just like your WhatsApp group where all the ECUs listen, but only act on messages which is meant for them, with like a high priority deciding who will speak first. Okay. So CAN is nothing but just a controlled area network. In this, it is two-wire communication. One is CAN high, and second one is CAN low. Okay. So these two wires carry the same signal, but in the opposite directions. Listen to me carefully, because this topic is like, if we have to learn about this topic in depth, it will take hours. Okay. So, but don't worry. At least you will get the overview or detail by the end of this session, and you will get the confidence about this. Like you may know about the CAN system. Okay. So let's continue. So these two wires carry the same signal but in opposite directions. Okay, so this is, we called it as differential signaling. Okay, this we called it as differential signaling. I will write it here. Okay. So, and it is what makes CAN resistance to like electrical noises, which is very important in EV with like high voltage systems nearby. Okay. And in the CAN, like every ECU on the network can send and receive messages. Okay. So in the the message are in the form of IDs. Okay. In the binary IDs number, in the form of binary data. So they have a priority IDs which gets generated when they whenever they, like whenever we have to press a button in our vehicle. So that creates some IDs, priority IDs, or the critical messages. Okay, so messages have priority IDs like critical message, like brake failure, which always get through first. Okay, so as you can see here, like how it actually works in a CAN communication line. Okay, here you can see that the BMS, here is our BMS, which is our battery management system. Okay, this is a good example of like how CAN communicates with the system. Okay, so here the BMS broadcasted a message like saying it is the state of charge. Okay, so suppose the state of charge is 78%, right? So that messages travel down the shared wire, which is our CAN high and CAN low. Here you can see the orange and the blue line. These are the two wires, which one is CAN high and second one is CAN low. So the message travels down the shared wire, and you can see here that every ECU, these all are ECUs, they all hears this message. Okay, but only the one that cares about the battery level, which is our motor controller. Okay, so like a motor controller and the dashboard part. So these two systems, these two ECUs really cares about the batteries SOC. Okay, and only these two ECUs will act on it. And here you can see that the thermal management system will ignore it. The message of BMS, the message it has sent the SOC, which is our 78%, thermal management system will ignore it. And why it will ignore it? Because it has, can anyone tell me why thermal management system, why it will ignore the message sent by the BMS, which is a the send of like SOC 78% the charge it has shown? Why it will ignore? Can anyone tell me? Okay, no issues. So in this, the thermal management system ignores it unless the battery temperature is evolved. Okay, unless the battery temperature is involved, that time the temperature of the like the battery, until the battery temperature will get high, thermal management system will not give attention to the message. Okay, so this is called as broadcast based or the message oriented communication here. Okay, there are some concepts like priority and the arbitration process and the differential signaling, how they works on the communication system or the BMS system, like the regenerative braking systems and thermal management system. Or there are so many of issues like in the ADAS system or the autonomous features, or we can say the auto start stop issue. Okay, if we will see here, you can see the priority and the, if we talk about priority and arbitration, okay, if two ECUs try to send a message at a same time, okay, that time can doesn't crash that time. Okay, so the message with the lower ID number wins. The message with the lower ID number will win. And why it will win, I will explain also in detail about this in the next slides, why it is going to happen, why it is getting the higher priority. Okay, just remember this, lower ID means higher priority. Okay, lower ID means, sorry for the like my handwriting. Okay, so lower ID means higher priority. Okay, this is why we call it as priority and the arbitration. Here you will see that the other ECUs backs off and wait. This is why like brake related signals always have lower ID numbers. Okay, and they are the critical ones. That's why they are getting lower IDs. Okay, and if we talk about differential signaling in the CAN bus, and like why it is really matters in the EV, because that the EV have powerful inverters like high voltage battery packs and the motors, and all these generating electrical noises. Okay, so regular single wire signals would get corrupted that time. So can two-wire differential system compares CAN high versus CAN low in this. So when any noise hits both wire equally, so it cancels out, and the signal which is inside the CAN bus will stay clean that time. So even better, like if one wire breaks, so that time the system can fall back to the single wire operation for critical systems. And the safety is also built in. Yeah, like you can see here the battery management system, which is our battery management system, it constantly broadcasting the messages like the in the cluster, in the EV cluster, like in the vehicle, we cluster in the cluster, we can constantly sees the battery like battery percentage or the battery health we can see in the cluster continuously. So this message is constantly broadcasting. Okay, so like the current charge is suppose the 72%, and the cell temperature suppose the it is around 34 degrees Celsius, and suppose the maximum discharge of current will be around maybe around 200 ampere. Okay, so the motor controller reads this and limits power if the battery is cold. Okay, so the dashboard shows the range estimation and like the thermal system which fires up cooling if temperature climbs in the battery pack. Okay, so this means like one message and three systems are responding at a time, and no direct wiring between any of them. That's how the CAN communication system is working. Same for the regenerative braking system. We will talk about regenerative braking system. Here we can see the ABS, which is our anti-lock braking system plus recovery. Okay, so like when the driver lifts up the throttle, if you know about like how regenerative braking system works, whenever we lift the throttle or the accelerator up, that time the motor becomes a generator. Okay, so this is how the regenerative braking system, that one I will I will not explain that much like part of about the regenerative braking system that much, but we are learning about today like the CAN network system, how regenerative braking system works here. Like whenever the driver lifts up the throttle, okay, the braking ECUs send a message like the enter into the regenerative mode. Okay, so that time the motor controller flips the motor to act as a generator. Okay, so the BMS receives confirmation that charging current is incoming, and like it adjusts it's the charging limits. Okay, so the dashboard updates the energy recovery display. Okay, and all of this happening in the milliseconds, right? As you can see that you are continuously seeing on the cluster the percentage of your battery. Okay, so these all are happening in milliseconds, and they are all they are all coordinating with the entirely through the CAN system here. Okay, and same for the ADAS system. We will see the ADAS system, the ECUs which are present in the ADAS system, autonomous features. ADAS, our ADAS platform is, what is ADAS? It is our Advanced Driving Assistance System, which helps us to stay on our lane keeping, automatic energetic braking, adaptive cruise, and they all are dependent on CAN system. For example, when you will see the radar which is present on the vehicle, it detects an obstacle. Okay, suppose you are running your vehicle is moving on a road, and suddenly your vehicle's radar detects an obstacle, and instantly it sends a higher priority message, which is our CAN message, the brake by wire system, which responds within the milliseconds that time. So CAN FT is typically used here because the data data like data from the camera, radar, or the leader feeds here, so it is too large for the CAN also here. Okay, and same for the the auto start stop button. Okay, here if we talk about in the hybrid EVs, the decision to shut down the combustion engine at a traffic spot at a traffic stop, you might have seen there are automatic, our vehicles get off at the after certain like few seconds, about 6 to 7 seconds, automatically on the whenever we apply a brake on our vehicle at the traffic stop. So that time if we talk about in the hybrid EVs, the decision to shut down the combustion engine at a traffic stop, so it requires like input from the vehicle speed sensors, right? So or there are many issues like from the battery, it also needs that like SOC and the load and the steering angle, the all these sensors, the data it collects from all the sensors. So all of these are collected via CAN and processed centrally. Okay, so without the CAN, you will need direct wiring between every one of those sensor and the engine controller. Okay, so in an EV, there is no mechanical linkage between systems the way there used to be in the older cars. Okay, everything is software and like software which is communicating over the CAN bus. Okay, so these all systems, how they are communicating the like with the help of ECUs or the many microcontrollers which are present inside the ECUs. Okay, so all these are happening under the 10 milliseconds or two thin wires. Like maximum, it has CAN high and CAN low. So these two thin wires are communicating, and all these communications is happening in under the 10 milliseconds. And that's why CAN bus is not just like a automotive protocol. It is like a foundation for every modern vehicle today. If you will see on the market. Okay, so especially critical in the EVs when the entire power train is on electric. Okay, so I hope you might get idea about what really CAN is. Okay, so before getting into more depth, okay, so let's see like how it arises, and nowadays like everyone is dependent on it, right? And to make simpler things, like you can see here, first, the origin of the CAN is started from 1983 to 1986. Here you can see. So basically, it is developed by Bosch. Basically, it was developed by Robert Bosch. Okay. So Robert Bosch in 1983, and officially it was introduced in 1986 at the automotive conference. Okay, but the main purpose is that time to reduce the complex wiring and and to enabling the communication between the ECUs. There is nothing that much more purpose of that time, because they just want to reduce the complexity. Okay, so then there is the first implementation you can see in 1987. The first CAN chip, which was launched by Intel and Philips in 1987. Okay, and the first car which is using this CAN controller chip is Mercedes-Benz W140. It becomes the first production vehicle with a CAN-based wiring system. Okay, so then, and it is arising like so fast, as you can see in the 1993, you can see here it gets ISO standard. ISO means International Organization for Standardization. ISO is International Organization of Standardization. So it was standardized in 1993 and under the number ISO 11898. Okay, so and after this it was gets splitted into three parts. And after this 1993, it was split into three parts like ISO. Sorry, let me rub here. Just a minute. And it was get split into three parts like ISO, and all of these have different workings. ISO 11898, then the ISO 11898 same for the 11898 they are splitted into three parts. ISO 118981, then 2, and then 3. And first one is for the data communication. Do remember this? First one is the data is for the data communication, and second one is for the high speed CAN. Okay, second one is for the high speed CAN, and third one is for the low speed CAN. Okay, so they get splitted into the three parts. Like first one is for the data communication, ISO 118982 for the high speed CAN, and ISO 118983 for the low speed CAN. Okay, then after this, a CAN Bosch released new, like a better version of this CAN system, which is our CAN FD 1.0. CAN FD is nothing but just a flexible data rate. CAN FD is CAN flexible data rate. Okay, so it was released in 2012, and the main improvement in this CAN FD is like in this we get the faster speed or the more data in one message. Okay, but it was compatible with older CAN system. Okay, so next, in 1996 onward, CAN is one of the protocol which is used in OBD, which is our onboard diagnostic vehicle. Okay, so after this vehicle diagnostic system is mandatory in many countries. Okay, so this is how the CAN arises in the past years. Okay, so CAN was just evolved from the like simple wiring solution, like to a, you can see right now, it became a global standard. ISO, you can see here, the International Organization of Standardization for vehicle communication, and today it is like a backbone for all modern vehicles. Okay, just do remember all these points. Okay, one for data communication, second for high speed CAN, and third for the low speed CAN. Then let's understand about the different versions of CAN system and what are the main difference between these three CAN systems. Okay, first one we have here is the CAN 2.0, which is, we also call it as the classical CAN. Second one we have, it is our CAN FD, which is flexible data rate, and third one is the CAN XL. Okay, so in the generation 1, if we talk about generation 1 CAN 2.0, okay, here the main thing is the identifier. You can see here, like it is using 11-bit identifier, and the identifier is like a message or like a address tag with 11 bits. Okay, so you can have like 2000 plus unique message IDs for a for a simple vehicle with a handful of ECUs. Like that is more than enough. Okay, so similarly, identifier means shorter frame and the faster transmission. Okay, so it was also divided like CAN 2.0 was also divided like CAN 2.0A, which is 11 bit, and CAN 2.0B, which is our 29-bit identifier. Okay, so it was also it is also has two variant, one which one has 11-bit identifier, and second one has like extended one, which is 29-bit identifier. Like with 29 bits you will get over like 500 plus million unique IDs here. So the question main arises here, like why does that matter for an EV? Why does because like if you will see in complex vehicle networks, like multiple CAN buses, dozen of subsystems, or like shared diagnostic tools, so there you need a much larger address space. Okay, so uniquely identifying every message from every node without conflicts. So that's why where we have used the CAN 2.0B, which is our 29-bit identifier. So CAN 2.A devices can talk to CAN 2.B devices, but not the other way around. If you will see, like 2.8 devices doesn't know how to read a 29-bit identifier. Okay, because it sees the longer frame, and we will also discuss what is frame in the CAN system in the next slide. Okay, so the thing is that it sees like a longer frame or triggers an error that time. Okay, so this is really compatible issue when mixing old and new hardware on the same bus. Okay, so the one is our CAN low and versus if you will see like the CAN high or CAN low, it is about like the fault tolerance for like the fault tolerance thing. If you will say like high speed CAN speed, okay, CAN speed is like transmitting speed at a data the maximum data the maximum data or the frame is 8 bytes, and the data rate of the speed of this CAN is 1 MB per second, 1 Mbps or 1 megabit per second. Okay, so it is used for critical systems. If we will like we are saying about CAN high, it is critical systems like battery, braking, motor control, which is used in the CAN high, and where speed is essential part. Okay, so and if we will talk about CAN low, if we will talk about CAN low, it has only speed of 125 kbps. Okay, CAN low has a speed of only 125 kilobit per second, and it is just comfortable for systems like windows, mirrors, and lightings. Okay, so the main key advantage of like the low speed CAN is if one break wires one wire get breaks. Okay, and each node has its own termination resistor in this. Like, can anyone, like whenever the wire get breaks, but still the message will get conveyed to the other wire here. Okay, so the system lives along either like the falling completely. Okay, and if we will talk about the CAN FD, which is our flexible data rate in the CAN system, the main problem here is like in the modern EVs. Imagine, if you will imagine like ADAS system, which is our automatic driving assistance system, that radar needs to send 48 bytes of object detection data. Okay, suppose it has detected a object while the vehicle is moving. Okay, so that time, imagine your radar system needs to send 48 bytes of objection detection data. So in CAN 2.0, you can only send 8 bytes per frame, right? So you need 6 separate frames, each with like own header identifier. I will show you how the CAN frame looks like. Okay, this is how the CAN frame looks like. I will explain about this in detail. Okay, so just know about this, how it works. Okay, so here, so you need like 6 separate frames. Okay, so each with like own header identifier and end of frame bits. Okay, so like that is a lot of overhead for one sensor reading. Okay, so here the CAN FD resolve all these things. Okay, the main first, there are like two innovations in this. Okay, like two speeds in one frame. Okay, like two speed in only one frame it gets. In this we will get. Okay, so in CAN FD, like it uses a slow speed during the arbitration phase. Okay, can anyone tell me what arbitration is? Anyone know? Anyone know about arbitration? Okay, no issues. So where we were? Okay, so in this, like they have developed, like they have done two innovations here, like two speeds in the one frame, and second one is 64 bytes. The maximum data or the frame we will get in is 64 bytes here. If we will compare with the CAN 2.0, in this we will only get only 6 byte here. But this CAN system, this CAN 2.0 has made a legacy. Like currently, if you will see in the like almost every vehicle, it is using the CAN system, not the CAN FD. Okay, But the main purpose of this CAN FD is like it the message, like if we will take an example of Tesla, it has maximum more than 70 plus or 100 plus sensors here. So there the messages or the number of IDs that create that time will be higher. Okay, so the maximum frame rate or the data rate we will need that time, or also the speed is matters here, because the date at what speed you are sending the message in the CAN system. Okay, so in this you can see here we can get a speed up to 5 megabyte per second. Okay, this is particularly important in EV because the arbitration phase needs to work like reliable evenly in electrical noisy environment like high voltage inverters. We will say like the data phase, and because the data phase cannot afford to run fast that time, because in the heavy vehicles system the high voltage wire creates noises, so our message get maybe maybe the message we are conveying from the battery to the cluster part may get error. Okay, so the second innovation was 64 bytes here. Okay, and instead of 8 bytes, one can frame ID can carry up to 64 bytes here in this. Okay, for that like same 48 byte radar reading. So what will that mean? Like when two frames in CAN 2.0 now takes just one frame. Okay, means less bus traffic, right? And the latency will be lower, and the bandwidth which is spread up on the like the bandwidth spread up for everything else here in the CAN FD system. Okay, so one thing like that makes CAN FD very practical for the EV manufacturers, it is backward compatibility. Okay, so CAN FD devices can coexist like on the same buses as CAN 2.0 devices. Okay, so new hardware gets the speed benefit in this. Okay, and the old hardware are still working, right? So like you don't have to replace the entire network at once. Okay, so the main thing is that the speed and the maximum data rate or the frame we are getting in the CAN FD is very higher than the CAN 2.0. Okay, and where you will find all these where you will find the CAN FD in the EV is maximum on the ADAS sensors. Okay, because ADAS sensor uses radar or the UV ultrasonic arrays. Okay, or the maximum you will say this CAN FD in the battery management system or the cell monitoring system. Okay, and there are some software updates like OTA, over the air software updates, you will see there the CAN FD working. Okay, so the next one is our CAN Axle. Okay, this is the newest generation CAN system. You can think of CAN Axle as a bridge between the CAN world or the Ethernet world. Okay, so like in the modern EVs, if you will especially those with the autonomous driving features are starting to generate so much data that even CAN FD can't keep up with. Okay, so a single forward facing camera generates gigabytes of data per hour. Can you just imagine generating a message of gigabytes per hour? It will how much the speed rate it will require, the frame rate it will require, but still there a single forward facing you will if you will see that the a single camera is generating a so much gigabytes of data, and there are so many cameras which is present on the autonomous driving vehicles. Okay, so that's where the ethernet or the automotive ethernet enters here. Okay, so but Ethernet doesn't have CAN collision resolution in the CAN Axle. like it uses a different arbitration mechanism, and it is deterministic for like real-time safety or the critical signals. Because in the autonomous driving system, we will take an example of Tesla. There is no driver which is running the vehicle. Okay, but all these is working with the ADAS system or the sensors which is present in the vehicle. Okay, so it is continuously communicating with the whole vehicle and communicating with all the system which is present in the vehicle. So they are generating real time data. Okay, and the latency in this system is much lower, like in the minimum 10 ms or the 5 ms maximum we will get latency in this system. Okay, so this is what makes CAN Excel special here. Okay, so if you will see like CAN Excel, okay, the CAN Excel is sorry, if you will say like the software. Okay, some maybe you have heard about the software defined vehicles. Okay, if you will take an example of MG Hector. Have you seen MG Hector? There is a in the rear side of the MG Hector, it was written as Internet Insight. Okay, it was written as Insight. That protocol is also, we call it as the V2V protocol, vehicle to vehicle protocol. Because in this vehicle, the technology is used as they have made their own network. The vehicles are communicating with each other. Okay, this is our vehicle to vehicle protocol here. Like if we take an example of MG Hector, because they are communicating with all the they have made their own network in which they are communicating. Okay, so that's same for the software defined vehicle. Because maybe in the future EVs won't just have pre-programmed ECU, they will run dynamically software that can be updated anytime. Okay, so the single most important thing is that all three generation can coexist on the same physical, but on the same physical bus. Can you just sorry? Okay. So a CAN Excel controller can still communicate with 2012. If you will see the 2012 era CAN FD. Okay, but this backward compatibility is what makes CAN dominance or the so durable. You don't rip out or replace your layer on the top. Okay, this is the versions which is currently on the market in the vehicles right now, which is sorry, one is our CAN and second one is our CAN FD, and the CAN Excel is the maximum sorry, the maximum in the vehicles here. Okay, so let's move forward. And here you can see the applications of CAN bus in a vehicle. Okay, like you can see here, the CAN bus act as a central communication backbone for a modern vehicle. Here you can see the vehicle is in the center and all the subsystem which is connected around it. Okay, and here you can see that the middle we have CAN bus, right? In the middle we have CAN bus. It connects all the ECUs. You can see all the ECUs are connected with this CAN bus here, right? So it connects all the ECUs with like two wire communication, which one in which one is our CAN high and second one is our CAN low. Okay, and it allows real time data exchange, like no direct wiring between each system, because it reduces the complexity. Okay, so like instead of 100 wires between the system, we use just two wires. That is the power of CAN. Okay, and you can see here the top layer, which is high level vehicle functions, like the ECU. You can see here the ECU these issues don't work independently. They like constantly talking to each other through the CAN bus. Okay, and you will see the sensors from the here. You can see here the camera, radar, and the ultrasonic sensors. Okay, so for example, radar detects an obstacle, sends data. Okay, and ADAS ECU will process it and it will send command to the braking system. Okay, and that's how the sensor are giving messages, signals to the CAN system, and the other subsystems are then the other system will start working on them. Okay, and all these systems are all the ECUs are present in this CAN system. Okay, and all the ECUs which are present in the or connected with the CAN bus, here you can see all the systems are connected. Okay, now let's, the main thing is our 7-layer OSI model. Okay, so let's first understand why engineers using a layered model at all. OSI means open system interconnection. OSI means open system interconnection. Okay, I will write it here. OSI is our open system interconnection. So engineers, why they are using the layered model? Because like engineers making things very the why engineers are making this bike, because they want to reduce the complexity of the wires, right? And the system which is very complex, they want to simplify them, right? So that's how they have built a 7-layer OSI model, which is our open system interconnection. Okay, so if we see in the networking, engineers use this OSI 7-layer model as a universal reference framework. Okay, and that separates the concern, like standardized each layer independently, and they let them work together cleanly. Like if you will see that the CAN, here you can see only the 2 layers are working here. Okay, and the rest are just for the high communication. I will explain also that. So CAN does not use all these 7 layers. It just primarily uses layer 2, which is our data link layer, and first one is our physical layer. Only CAN is only using 2 layer. One is our physical and second one is our data link layer. Okay, so CAN bus lives in only in the layer 1, which is our physical layer. Okay, and the layer 2 is our data link layer, and layer 3 to 7. Here from you can see that layer 3 to 7 are handled by the higher level protocols, which is built on the top of the CAN, like the UDS, onboard diagnostic system protocol. Okay, and there are many more systems protocols like J1939, which is basically in the used in the trucks. Okay, they are using the other above these OSI model layers. Okay, so and there are so many protocols like CAN open also. CAN open, this one protocol is used in the industrial systems. Okay, so let's break down this like how these sublayers are coming, how these CAN sublayers are working. Okay, so here you can see that the ISO 11898 I just mentioned previously in the slide. ISO 11898 892 and 11891, right? So this is the data link layer. This is the data link layer here. Basically, this is the main intelligence of CAN. Here the CAN smartness lives. If you will see that the 3 sublayers handles it. Okay, the sublayer 1 is our logic link layer. Sorry, logic link control. This one is our first sub layer in a CAN system, because in any CAN network, every ECU receives every message on the bus. Okay, so the LLC here, the logic link control here, uses message filtering. Okay, so all they are doing the message filtering in this. The message which is relevant to them, only it receives that message. Okay, see the logic link layer working here. Like if we'll take an example of in an EV, like imagine suppose the dashboard ECU receiving like the 100 of messages per second, like from the battery or the motor status or the thermal readings, suppose for the door sensor updates. So there the LLC filter says like I only care about, suppose it doesn't need any need things like, it only cares about the messages with IDs only related to battery or the state of charge and the motor speed. Okay, and every message which is not relevant to them, it will ignore it. Okay, so what LLC handles here is acceptance filtering. First is acceptance filtering, which means ID, like message ID, the nodes which are present in the ECUs or the CAN system. What they do here, the node should process the message ID there. Okay, and second one is overload notification, means whenever the signaling or any ECU which is too busy to receive more frame immediately. Okay, so that is the overload notification. Then third one is our recovery management. Like what recovery management does here, like it manages re-entry after an error. Like suppose your message get errored by any high voltage suppose high voltage noise, because in the heavy vehicles we use high voltage system. So the high voltage systems, the noise created by the high voltage system, it disturbs the message of the CAN system. Okay, so there the recovery management works, like it manages and they do the re-entry after any error occurs in the system. Okay, and then the second layer comes here, which is our media access control and MAC. Okay, so like this is the core of CAN standard. Okay, so like most of what makes CAN reliable basically happens here. Okay, in the media access control. So what really here the Mac handles here, which one is our arbitration and second one is frame packaging and like error coding and or acknowledgement. I will just I have showed you the this frame rate. Here you can see the acknowledgement and other things. I will explain also you in detail about this. Okay, so arbitration, like when the BMS and the motor controller both try to send a message at the exact same moment, that time the MAC arbitration process it and runs a wired AND. Okay, it processes a wired AND there, and the comparison of their message IDs bit by bit means the message with the lower ID number, it will win there. Okay, and it has the higher priority and it continuously transmits that time. Okay, so the other issues detect and the other issues, when they will detect, it lost the data that time, and there will be no collision or no data loss, or like there is no supervisor needed for that, because the collision is not happening there. The arbitration helps to get the message ID bit by bit to the main system. Okay, the second one is here is frame packaging. Okay, frame packaging means the Mac here wraps array data into like a proper structured CAN frame. Okay, like the frame starts from SOF, start of frame. Okay, then the identifier comes, then after the identifier the control field comes, and after the control field the CRC, like putting if we will see that like putting a letter in a properly addressed or like in an envelope here, this is how the CAN frames work there. So if you will see the like error detection also handles handled by the MAC system. Okay, so the MAC runs 5 simultaneously error checking mechanism, okay, on every single frame. Like if even one bit is wrong, the error is caught by the MAC. Okay, so then after this, the acknowledgement happens. Okay, so after a frame is sent, the message wait for at least like one receiver or like on the bus to confirm it, and it received the message correctly by the like by pulling the ACK slot. I that like just I have showed you the CAN frame. Okay, so if nobody acknowledges, so like something is wrong inside this system there that time. Okay, so this is what about the this is just about the MAC system. Then the third sublayer is our physical coding. Okay, this is the third sublayer, and the physical layer, it is like the translator. Okay, it works like a translator who converts like your written message into the code. Okay, because for the transmission we need a code. Okay, so then they just convert the code and like back into the words for the other end. Okay, because we also want, because we can't see the battery percentage in the form of code. Okay, so we also need a word for that. Okay, so the sub layers here the handles the conversation between the logical bits. Logical bits like 0 and 1. This is our binary number as well, 0 and 1. Okay, so the PC here, the PC handles the here the logical bits. Okay, which is our 0 and 1. Like Mac also works with and like actual electrical signal patterns on the wire here. So if you will see about the bit coding, bit encoding is nothing but just a converting a logical 0. Bit encoding is nothing but just converting a logical 0 into a dominant state. Okay, so that means suppose a CAN high has 3.5 volt of power and the CAN low has 1.5 volt. Okay, here the 0 is our, here you can see that the 0 is our dominant one and 1 we call it as recessive. Okay, so the bit timing ensures every ECU on the bus like it for the sampling bits at the like exactly the right moment. Okay, and also in this the synchronization also happens there, because like keeping all nodes in a sync, so a bit sent by the BMS at a node A is correctly received by the motor controller at the node B. Okay, so even if the like the clock drifts slightly in the ECU or sends the message, okay, that time synchronization happens. Okay, and as you can see here the ISO 11892, this is our physical layer, or we can say the body of our CAN. Okay, so if the data link layer is CAN intelligence, the physical layer is its body. Okay, so the actual hardware that touches electrons is our CAN physical layer. Okay, or we can say the physical sub layer, fourth sub layer. Okay, so this is our physical media attachment. Okay, so the physical media attachment is like a loudspeaker or a microphone. Okay, like it converts digital signals into physical voltage on the wires. Okay, and the when they convert the digital signals into the physical wires on the physical voltage on the wires, and the data they get, it converts voltage level backs into the digital signal for the receiver as well. Okay, so this is like a CAN receiver chip. Okay, so like a small integrated circuit present at every node in like in your AV, or every ECU has one this. So when transmitting the trans receiver, it takes a dominant command from the MAC. okay, and drives the CAN high towards a CAN high, we have the 3.5 volt, while simulating pulling CAN low towards creating a differential voltage of 2 volt. Okay, so when receiving it, it reads the differential voltage between CAN high and CAN low. Okay, and why differential voltage matters in a EV? Because EV's inverter generate enormous electrical noise. Okay, so a single wire signal would be corrupted in milliseconds. Okay, so but differential signaling compares the difference between the two wires, and any noise that hits both wires equally cancels out completely that time. So this is why CAN works reliably even right next to a 400 volt battery pack and a high frequency switching inverter. Okay, still the message generated by the any ECU in the CAN system, it won't get disturbed. Okay, so you get a proper message at proper timing. Okay, so there was not a delay at that time. So the next one that is about the physical media attachment, and last one is our physical media dependent. Okay, so sorry. So like if physical media attachment is like a loudspeaker, I just have gave the example about this. So suppose this physical media dependent is like a room. Okay, and like a acoustic design, the physical medium that basically carries the sound waves. Okay, so this is the actual wire here. The CAN system has twisted pair of wires. It has a twisted pair of wires just to reduce the noises. Okay, so this is the actual twisted pair cable here, which is our physical media dependent. Okay, so and its termination resistor, this is what you would physically hold in your hand. Okay, and the twisted pair here, the CAN high and the CAN low wires are twisted together, typically about like 30 twists per meter. Okay, so twisting ensures that any electromagnetic interference hits both wire at the almost exactly the same time, and they all form the same angle that time. Okay, so like maximizing the noise cancellation that gives the benefit of our differential signaling in the CAN system. Okay, so here here you can see that this is our this is all about sorry this is all about the 7-layer OSI model. Okay, now let's understand about how node architecture basically looks like. Okay, so I think before understanding this, we must know about the data transmissions. Okay, here you can see the dominant bit and the recessive bit. Okay, let's first just understand about this dominance or recessive. So CAN basically uses two states: dominant, which is our 0, and recessive means logical, okay, which is 1. Okay, so dominant means at least one ECU is actively driving the bus, okay, or pushing the CAN high to 3.5 volt and CAN low to 1.5 volt. So the differential voltage is around 2 volt here. And recessive means nobody is driving the bus here. So the voltage, the 120 ohm termination resistor passively pulls both wire to 2.5 volt. So the differential voltage will be 0 volt there. Okay, so the critical rule that makes arbitration work is dominant, because the dominant always wins over recessive one. Okay, so like if one ECU is transmitting a 0 and another is transmitting 1 at the same bit position, okay, so the bus shows dominant. Okay, because the ECU transmitting 1 and it detects the conflicts and knows like it lost the arbitration and it will automatically get stopped that time. So this is wired and principle. Basically this works on the wired and principle. So the bus behaves here the bus behaves like a output of an AND gate, okay, which is fed by all the transmitters. Okay, so suppose the emergency you have applied the emergency braking. ECU has an ID of, suppose we ECU has an ID of 0 into like 001, suppose. So all the dominant bits. So the if you see about the infotainment system has suppose it has a ID of 0 into 3. Okay. So these are all the recessive bits here. So in collision, the braking message physically overrides the infotainment message on the wire, not by the software logic, but by the physicals, but by the physics of the electrical circuits here. Okay, and high power versus low power, you will see that the high power and low power both ends are connected with, like one end is node A and second one is the node B. Okay, just a second. Okay, so there are some high speeds and CAN low. Okay, and CAN I just have mentioned you before that the CAN high speed uses 118982 and CAN low is 118983. Okay, so in the CAN high we have 1 megabit per second or like 8 megabit per second or frame rate. Okay, so it uses a linear bus with exactly 120 ohm resistors at each end. Okay, so which is used for all the safety and like powertrain systems or the motor controller, BMS, airbags. Okay, so all these are working with node A to node B in the CAN high speed. Okay, so in the CAN low speed, which is our fault tolerant CAN or CAN like ISO 118983, the speed we get is around 125 kilobit in this CAN low, right? Kilobit. The speed we get is kilobit. So instead of two central termination resistor, each node carries a fraction of termination resistance internally here. So this means if one wire is cut or shorts to the ground, okay, but the system detects the fault and continuously operating on a single wire that time until you will see that the used or for body control modules like windows, mirrors, lightings, where losing the network entirely would be unacceptable, even if you will live along at the reduced speed. Okay, like for an EV, think of this way. Like high speed CAN is the motor way, like fast or efficient, which requires which requires the road to be intact. Okay, for the low speed CAN is the back road, which is slower. But if one lane is blocked, you can still get through. Okay, so the main thing is just when your EV, suppose when your EV BMS detects the battery temperature is rising and sends a reduced power. So it sends a command to the motor controller, and here is the complete journey. Like you will see that the applications layer and presentation layer, session layer. So all these are working. Okay, so this is how the dominant and recessive bits works there. Okay, only the message with the lower ID will gets the higher priority in the CAN system. Okay, so now let's understand about the node architecture. Okay, so here you will see, if you will see that sorry, you can see that the host processor. So in this basically this is our nodes architecture here. The microcontroller is basically the host processor here. Okay, the microcontroller is the main host processor here. This is the we also call it as host processor because it acts as a brain of the node, and it decides what the received message mean, or what data need to be transmitted. Okay, so it is also connected with the sensors input devices sensors inputs, or the actuators like output devices, okay, or the control systems here. So this is the microcontrollers or the host processors. So all the real world signals are processed here in the microcontroller. Okay, then comes our CAN controller. This is the second component in the CAN controller, which is often built inside the microcontroller. The main function or the receiving function of this CAN controller is just it collects the incoming data from the CAN bus and converts them into a complete message frame. Okay, and also notifies the host processor usually when they get interrupt. Okay, and the second function of this CAN controller here is transmitting function. Okay, one is receiving function and second one is transmitting function. Okay, so the host processor sends data to the CAN controller, and the CAN controller formats the message, and here it handles the arbitration. Okay, and then sends the data serially onto the CAN bus when the CAN bus is free. Okay, so the CAN controller manages protocol level operation here. Okay, then the third one is our CAN transceiver, which is our, also we can call it as physical layer devices, which is physical layer devices. Okay, this one is our CAN transceiver, the third component here. So here you can see it is defined by ISO 11892 or 3. Okay, means CAN high or CAN low, they both support this. So it basically converts the electrical signals from the CAN bus into the logical signals. Okay, and passes them to the CAN controller. Okay, and also it provides protection against the noises or the voltage spikes in the message IDs. Okay, means when they when they convert the logic signals from the CAN controller into CAN bus voltage levels, it sends them onto the CAN high and CAN low. Okay, so the transceiver handles here the electrical communication. Okay, and now let's understand how basically the message communication works here. Is each node can send or receive message, but not at the same time. Okay, so how can frame structure here looks like, we will see on the next slide. Just okay, we will see on the next slide. Where is it? Oh, this is how the CAN frame structure looks like basically. Okay, this is what the frame, here you can see the IDs, identifiers, data fields. Okay, here you can see the CRC field. I will explain you all of this because this is the main part. Okay, because we are not doing the coding or the calculations here, we are just getting through the overview of this, basically what really CAN is. Okay, so this is how the CAN frames look like whenever they send or receive message. Okay, this is how the message is looks like in the CAN frame. Okay, so it is nothing like just a CAN node consists of host processor or a CAN controller or a transceiver. So basically here the processor makes decision, or the controller handles the communication logic, and the a transceiver manages electrical signal conversion together. Okay, so they enable reliable data exchange across the vehicle network. Okay, So now let's understand how arbitration works there. Okay. So in any communication network, sorry, what I'm saying here. Sorry. So the main problem is the hardest problem is to solve is contention. What happens like when two senders transmit simultaneously? Like different technologies solve this differently. As you can see here, the CSMA. Basically, CSMA is nothing but just a carrier sense multiple access. Okay, this is nothing but just a carrier sense multiple access with collision detection. Okay, collision detection. So this is nothing but just a CSMA, which is basically it is a media access control, or we can also say that the MAC protocol. We can also say the MAC protocol here. This is nothing but just a carrier sense multiple access with collision detection. Basically, it is like a MAC protocol which is used in the older shared like Ethernet networks to the Ethernet networks to detect and manages the data collision by like monitoring the transmission medium and stopping the transmission if a collision occurs inside the message. Okay, so in this it detects the collision, okay, and stops everyone and wait a random time, then it will again retry the message. Okay, and if data get lost and must be, suppose the message may get lost at time because the data might get collide. Okay, so the when the data get lost, it resent continuously or randomly that time because the function needs to be worked that time. Okay, so basically Wi-Fi uses this type of protocol which try to avoid the collision before they happen by listening first. Okay, so CAN uses here the something far smarter like for real time system, lossless bitwise arbitration. No data is ever lost, like no delay to the higher priority message, and it all happens automatically in hardware in microseconds. Okay, and I just have showed you the this system, the dominant system, and the both है सर थोड़ा शिफ्ट भी रखेंगे. So basically the thing is that the okay, so basically the thing is that the node or sorry, the node here, the node A or node B, you can see the dominant and the recessive one. Okay, so these are the two states of the CAN bus. Okay, one is recessive and second one is the dominant one. Okay, and this is how the arbitration fields look like. Okay, so when the lowest ID here, you can see the all the numbers are 000, then 1001. This is the this is the ID which is created by the node A, and this was the ID which is created by the node B. And here you can see the dominant one is our 0 and the recessive is our 1. Okay, so node 1 here is become the recessive, but here you can see the node A becomes dominant because it sends a ID with 0 continuously here. Okay, so maybe suppose this node A, suppose the message we get from the node A is from the braking system. Okay, so that times here it becomes the dominant one and it will act first before acting the different ID. Okay, so this is how the node A and like bitwise communications looks like in the CAN system here. Okay, so like when the engineers like assign CAN message ID in a vehicle, we will see that they give the most safest critical message with the lowest numbers, because in emergency braking we need a dominant message or dominant ID. Okay, so and for also the airbag systems, which works very quick while colliding with any vehicle or striking with any vehicle. So it is a critical message which can never be blocked by the lower priority traffic here. So okay, so even at the peak bus load, it sends the dominant message there. Okay, then the next thing is our synchronization. Okay, if we will see that the synchronization, here you will see that all the nodes which must sample at the same time. Like for arbitration to work, every node on the bus must read each bit at exactly the same moment. Okay, suppose if node A reads bit 4 slightly before the node B. Okay, suppose, just give me a second. Okay, so suppose if node A reads bit 4 slightly before the node B, they might see different values. Okay, and the whole arbitration that time or the logic will break down that time. Okay, so the can achieve this without a dedicated clock wire. And how it will work? Because instead every node uses the transitions in the data stream that time. So the edges between the suppose the edge between the 0 to 1 or 1 to 0 to continuously resynchronize their internal clocks. Okay, so each bit is divided into time segments here. So the sample point is the agreed movement. Here you can see the sample point is like a agreed movement when every node reads the bus value. Okay, so by adjusting the phase, buffer segment or the each node can compensate for small clock drifts. Okay, so the syn segment is where nodes realign their clocks, and whenever a transition occurs on the bus like 1 to 0, it will happens automatically there or manages there. Okay, so this is why the spec says can is synchronous in behavior. So everyone samples at the same time but asynchronous in format. There is no separate clock wire for any message ID. Okay, so they both are correctly dependent on their how they are sending the message and which message ID has the dominant number like the 0. Suppose the ID number with 4 zeros will get dominant automatically if you will compare with this one. Okay, so this is how the synchronization happens in the which happens inside the ID which is created by any ECU on the network. Okay, and here you can see the speed, which is 1 megabit per second. Okay, so here you can see the speed which is 1 megabyte per second or 1000 nanoseconds here. For you can see at the maximum 40 meter here, it is talked about the actually the wire. Okay, the length of the wires. Suppose if you will run 1 megabit or 1 million bits of data which is transferred which is getting transferred per second over a 500-meter bus, suppose. Okay, so that time propagation delays would be around maybe half of that nanoseconds. Suppose we have 5000 nanoseconds, it will be get automatically half that time, like around 2500 nanoseconds in that time, because the speed will automatically get reduced. So longer than 1 bit period by the time or dominant bit from one end reaches the other end or the sample point, just like this here. So that time it already passed the arbitration. Okay, so that time it is the sample point has already passed that time and the arbitration will get failed and will get failed that time. Okay, suppose for a modern passenger car, there is a 4 to 5 the modern cars like 4 to 5 meters long. Okay, so like even with the wiring routing through the chassis, a 1 megabit per second CAN bus comfortably covers the entire vehicle. Okay, so the 40-meter limit is never a concern inside a single vehicle. However, like for any like any charging station network or a fleet of connected trucks, engineers must carefully design both the topologies or the CAN FD, because the CAN FD has the maximum speed rate. Okay, and right now it is getting widely used in the vehicle because CAN 2.0 is becoming less, because just about the sensors or the technology which is getting developed so fast. Okay, so there are many companies which are using CAN FD as well, like Mahindra. Okay, so here the CAN FT is like an elegant solution to the maximum speed problems. Okay, because CAN FT solves the speed distance tension by like separating the two phases. Like they have different requirements, because during arbitration multiple nodes are competing, because so the bus must be long enough for signals to propagate to all the nodes, because the sample point here you can see that all the nodes read bit here. Okay, so that means that all the like CAN FT keeps arbitration at the slower 1 megabit per second. This respects the physics. Like after arbitration there is now only one transmitter. And how they are becoming one transmitter? Because propagation delays is still the same here, but the main thing is there is no competition. Okay, so the timing only needs to work for only one center and multiple receivers. Okay, so that time CAN FD then switches up to 8 MB per second. Okay, and if we will take the CAN XL, it will give us the speed of around 20 megabit per second. So like just for the data payload, only the data is sent. Okay, so it switches back to the slower rate for the end of the frame signaling. Okay, so this is how. Uh, and if you will see the bit timing and how ID allocation, what exactly the ID allocation is. So every ECU in your in your EV has like it has its own like internal oscillator crystal, like a tiny vibrating component inside the in your ECU, like a tiny vibrating component in your ECU. It just gives the clock signals and the microcontroller uses to count it. Okay, so the problem is that no two crystals are perfectly identical there. So they manufactured with like small tolerance, they heat up differently, or suppose imagine the BMS is next to a hot battery pack versus the dashboard or the ECU in the cooler air. So they drift over time that there. So in CAN there is no separate clock wire. Okay, so like every node in this runs its own clock and must stay synchronized purely by just observing transitions in the data stream there. So like understanding how this work is why bit timing is all about. The here you can see that the first is previous bit, nominal bit here is it has 4 points. One is since, then prop, then phase 1, then phase 2. Then automatically the next bit will start from here, and here is the previous bit will get end there. Okay, so the main thing is the CAN 1 bit is not just 1 or 0. It is like carefully like structured time window which is divided into 4 segments like since prop. Okay, and the message ID which it will create must be unique on the single CAN bus. Otherwise, the two nodes would continuously transmission beyond the end of the arbitration field which will cause an error at the end. Okay. So this is how the bit timing looks like, or the ID, how ID allocation works. And now let's understand about this can frame. Okay. Now listen to me carefully, because this is like the main important thing, how the message structures looks like in a can frame. Okay. So here you can see that the communication over a CAN bus is done via the CAN frames. Just give me a second, I will drink some water. Okay. So this is the main thing. Like a CAN message is like not just sent as a only raw data. It sends in a proper frame. As you can see here, this is the proper frame is like a message is properly sent, fixed here, or like a envelope is made here. Let's start from here. Okay, the first, which is our start of frame. Okay, this is the first bit of the CAN message. Okay, like it tells all the ECUs on the CAN bus, like pay attention here, or like the suppose someone presses any button, so it will tells all the ECUs on the CAN bus, like you have to pay attention, a message is starting here from here. Okay, so before start of frame, the bus will be idle there. So when SOF comes, all the connected ECUs become synchronized and starts reading the incoming bits. Okay, then second comes our arbitration field, which has total of 14 bits, 11, then 112, 13, 14, which has total of 14 bits here. Okay, so this field, basically this field decides which message gets priority. Okay, so like if two ECUs start transmitting at the same time, it will contain 11 bit identifier. It will contain 11 bit identifier plus RTR, IDE and R0. What is RTR? Basically RTR is but nothing but just, I will write here, it is our remote transmission request. Okay, what RTR is? It is our remote transmission request. Okay, so this is the 11-bit identifier plus RTR plus RDA, IDE plus R0. So 11-bit identifier is the like most important part of the arbitration field, because, and why it is important? Because what type the message is, or what priority the message has, or like which data is to be which data is being transmitted. Example, for example, like a message is sended from the BMS. Sorry, a BMS has sended the message like the battery percentage would be around 50%. Okay, so the lower CAN ID equal to higher priority, I just have mentioned before. So that time ECU or CAN ID, or it will automatically create the priority time. Suppose I have pressed the brake or the door ECU, I have given the like command to the brake or door ECU at the same time. Okay, so that time brake ECU will get the higher priority if we will compare with the door ECU. Why? Because there is a high brake CAN high there, and the speed will be higher, and the action will be more fast in the braking time. Okay, so like if brakes data or data door status data are transmitted like at the same time, brake will automatically get spin because it is working on the CAN high. Okay, so like how arbitration works here, just I just have told you like dominant and the recessive one. Zero is the dominant one. Suppose whenever the message with the higher, with the dominant ID or the zero number will automatically gets dominant. Okay, so then the RTR is the remote transmission bit here. Basically it tells whether the frame is carrying data or requesting data. Okay, so RTR value means 0. Okay, I will write it here. RTR, the data means 0 is our data frame and 1 is our remote frame here. Okay. So RTR is remote transmission request. So it tells whether the frame is carrying data or requesting the data. Okay, so 0 is our data frame and 1 is our requesting frame. So like in most EVs or like auto, if you will take an example, like we mainly discuss data frames where actually data is being sent. Okay, so then comes our IDE, which is our identifier extension. So what basically identifier extension does, like it tells whether the CAN frame is standard or extended. Okay, what basically tells it here, the CAN frame is standard or like it is extended. So suppose it also works like 0 or 1. 0 or 1. 0 is for the standard frame, and 1 is for the extended frame. Okay, extended frame. Standard frame will be around 11 bit or the extended frame will be 29 bits ID. So this shows like standard CAN frame or it uses like 11 bit identifier there. And then comes our R0 or R0, you can say, like this is the recessive bit. Okay, so it is kept for protocol control or future use. So in normal classroom explanation, like uh, we will say that the student, like students like you, if you have to think about the the recessive bit or the recessive bit, in this the DLC means or the data link layer comes after the recessive bit. And how this is working here, like this is basically the data length code. It tells the trans receiver like how many bytes of data are coming in the data field. Okay, and the classical cans can carry here the 0 to 8 bytes of data. That means suppose here you can also see that 0 to 8 byte or 0 to 64 byte. 64 is for the CAN Axle and 0 to 8 is for the uh, FD or CAN FD or CAN 2.0, right? So data field is like 0 to 8 bytes. This is like actual usual information. Basically this one is the data field. It is the actual useful information in an EV. Like any data field may carry battery message or the motor message or the charger message. Any EV data can may carry all these messages. Let's suppose from the battery message we are like getting the voltage or current SOC, or suppose from the motor messages we are getting RPM, torque, temperature, all these things. Okay, then comes our, after this, the CRC field. But basically CRC is our cyclic redundancy check. This is our cycle redundancy check, which we also call as CRC. So basically this field is used for the error detection. Okay, so this is the main field which is used for the error detection, where vehicles having a noisy electrical environment, suppose like motor, inverter, relays, they create noises. Okay, so the noise may change a bit from 0 to 1 or like from 1 to 0 automatically at that time. So like CRC helps detect that error. Okay, so like how CRC works here, like the transmitter automatically calculates a CRC value from the message and sends it with the frame there. Okay, so the receiver also calculates the CRC from the received message. So if when the both values match, message is correct. Okay, suppose if they don't match, the message has an error and must be rejected that time. So the CRC is nothing but just like a separation bit after the CRC. Okay, so this is the CRC delimiter bit. Then after this, that comes our ACK, which is our acknowledgement. Okay, so basically there is nothing but just this field confirms whether at least one receiver has received the message correctly. Okay, like it has a ACK slot, and it only contains 2 bits of data. Okay, so it has only two. One is ACK slot, and second one is ACK delimiter. Okay, so like how basically it works here, like they transmit the transmitter, when the transmitter sends like a recessive bit in the ACK slot. Okay, so if any receiver receives the message correctly, it sends a dominant bit in the ACK slot. So the transmitter understand someone's received my message, like someone received my message successfully. So like if no ACK is received, the transmitter knows like there may be a problem, or the message may and the message can be retransmitted that time. Okay, then comes our end of frame, which is EOF. Basically it just tells all the issues that the message is completed here, and after the EOF, the issue know that the current frame has ended. And after this is the intermission, which is of around 3 bits. Basically it is nothing but just a small gap of nothing but just a small gap after the frame. It gives the CAN bus a short recovery time before the next message starts. Okay, so after this gap, another issue can start or send a new frame. Okay, so then here you can also see that the bit stuffing, there bit stuffing, here it is the bits without bit stuffing, and here is the stuffing part. Okay, so bit stuffing, like it is used to like to maintain a synchronization, nothing but just a synchronization in like in CAN. If the same bit repeats too many times, that time receiver may lose timing reference. Okay, so also can follow this rule, like after 5 consecutive same bits, the transmitter automatically inserts one opposite bit. Okay, for example, the original data is 111110. Okay, and after the bit stuffing, it will automatically become the like 111110. It will automatically become it has just automatically added the 10 more. Okay, so this is how it automatically insert one opposite bit to confirm the to make a priority or lower priority accordingly. Okay, so bit stuffing applies mainly from, you can see here, the start from the frame to the CRC part. Okay, you can see here the start from frame to the CRC part here. So after this, the CRC from the here, the CRC delimiter to the end of frame, it is our without bit stuffing. So there is no need of bit stuffing here, because in this the end of frame or the here it is the main error part, here is the acknowledgement part, and it is the end of frame part. Like the your message is your messages gets completed, and here it is the intermission, like it gets time to start the new message from here. Okay, so this is what how CAN frame looks like. Okay, and there are some there are some CAN bus or the adapters we use on the vehicles to extract the CAN messages or the data we need data from the vehicle. Okay, so you can see here you use an OBD2 adapter to connect. Okay, so in the cars we maximum use, or for the onboard diagnostic, we use OBD2 adapter to connect. Okay, so like almost like every modern vehicle you will see, they use OBD2 port. Okay, so this is how it looks like. This is our OBD2 adapter. So and if you want to see this on your vehicle, it will basically usually located below the steering wheel, or near the driver footwell. Okay, so the main purpose of this adapter is to like read the fault codes or monitor the engine data or like access. It gives like access to the CAN bus communication and also like the diagnose the vehicle problems there. So what data can be accessed like the battery voltage, vehicle speed, motor RPM, all this we can get from the with the help of this OBD2 adapter. Then second one, no, sorry, here you can see also the UDS, which is our Unified Diagnostic Service. Okay, so this is like an advanced diagnostic protocol which is used over CAN. Okay, so basically it is used for ECU programming or like fault diagnostic or like the updates whenever we go to the EV service we do some updates. So with the help of this adapter we can easily do the updates. Okay, so then next comes our is our J1939. So basically this connector or cable, this is this detached 9-pin cable. It is used on the trucks, excavators or the tractors. You can see here. So because if you will see why this is different, and because if you will see that the heavy vehicles are due to their high load or the vibrations we get from the high vehicle is much more compared with the normal passengers car. Okay, so that's why it is more like more rushed conductors, or it is better for the like vibration resistance. And like for the if we will see the industrial reliability, we use that's why we use this detached 9-pin connector in the heavy vehicles. Okay, and what it monitors there, it monitors the motor RPM, the pressures or the all the thing which is inside the trucks. Okay, then comes our Maritime M12 adapter to connect and log NMEA 2000 marine data. So this is maritime data means this is basically used in the ships or boats, or like also use CAN communication like they basically this is a protocol. Okay, so NMEA is 2000 is like a protocol which communicates the GPS or the radar system or the fuel system or the navigation system in the ships or the ports. Okay, so the M12 adapter is used to extract that data or because it is like waterproof or it is basically designed for the like moisture resistance or vibration protection. So that's why we use this type of adapter in the ships there. So then next comes our CAN open. CAN open, here you can see that basically this is used on the robotics or PLC systems. It is used in PLC system also uses this CAN open, or CNC machine also uses this CAN open CAN system. So the main purpose is nothing but just to allow the communication between the sensors, motors, controller, drivers. Okay. So the real thing is that the suppose a robot arm in a factory, the motor controller sends the position data or PLC sends the movement command. So everything is synchronized using the CAN open there. Okay. So then next come is our contactless. This is the contactless, or the we can also say it is as the CAN crocodile. Okay, like basically this device reads the CAN signal without physically cutting or connecting the wires. Okay, and now you might have a question like how it is working. So this CAN crocodile basically it automatically senses the radar system. Okay, so basically it just senses the radar signals with the help of CAN crocodile system. So there is nothing just to connect the wires inside this in this system. So it senses the electromagnetic signals around the twisted CAN wires. Okay, so then last one is our generic open wire adapter. So it directly connects to the CAN high, CAN low, and the ground wire. Okay. So now let's understand just will give you the overview of this LIN, which is nothing but just a local interconnect network. It is low communication system which is used inside the vehicles where very high speed is not required. Okay, so it is commonly used for the comfort and the body control function. Okay, so like this, it offers lower performance and reliability, but also like drastically lower cost. Okay, we will compare it with the CAN bus. It provide low cost options. Suppose basically the main function of this LIN is basically used on the vehicle is on the windows, wipers, air conditions. There we use the CAN system. Okay, it also works. It also has the 7-layer OSI model, and basically this LIN starts from the application layer there. Okay, so LIN is like a cluster which consists of like one master and up to 15 slave nodes. Here you can also see the architecture here. There is only one master ECU and all the slaves are connecting or communicating with only single master ECU there. Okay. So in most newer vehicles have 10 plus LIN nodes. Okay. So CAN uses 11 or 12 bit identifiers, but in LIN, if you will see that the LIN uses only 6-bit identifier. Okay, so CAN offers here up to 1 megabit, and LIN, the speed we get from the LIN is only 20 kilobit. Okay, so if we comparing it with the CAN system, so it is much lower. That's why we are using on the power windows and slave interior lights, seat adjustment, headlamps. There we use the LIN system. Okay, so basically its application is only on the steering wheel like cruise control. Okay. Sorry. And if you talk about comfort, only sensors for temperature like sunroof, light, humidity. Okay. And if you will say the powertrain, in the powertrain, the LIN system works only for the sensor for position like speed, brake, pressure. Okay. And if you talk about air conditioning, motor, control panel, all these things. Take care. So this is how the LIN architecture looks like. All the slaves are communicating with one master ECU, and this master ECU is giving communicating with the main CAN system. Okay. So this is what CAN is and what CAN bus in the BMS looks like and why it is crucial. Like it, we all know that it gives the real-time safety monitoring, coordinating with the powertrain components, and it also enhances the diagnostic and maintenance, right? And the compatibility with the charging infrastructure like fast charging onboard charging relay or it also gives exchange key parameters. Okay, and also allows us to save efficiently charge cycles. So this is all about cab bus. We all know. Okay, but in the CAN, if you will see that the common protocols CAN open is ISO 11898. So several standards operate over CAN bus here, but CAN open and ISO 11898 being like the most relevant for most mobility focused BMS design. Okay, so then here you can see the picture. You can see all the components names. Okay, first one you can see here the microcontroller. Okay, here is the microcontroller. This is basically the central processing like a CPU of the board. What it does, it runs the embedded software, controls all the system operations, processes sensors data, and also sends the received CAN or LIN messages. Okay, then second you can see here the high density board to board connectors. Okay, so what they are basically, they are you can see that the large black connectors on the top. These are the large black connectors on the top. Its main purpose is just to connect this board to the another board like a daughter board or the interface module. Okay, and why they are needed? Because for the modular design, कितने students बचे हैं? So if we see about the microcontroller or the high density things, because in this easy testing or the replacement we need that time we use these connectors. Okay, so voltage regulators and power management, we will see that the voltage regulator, and these are the ICs which are used in the BMS, and the high voltage contactors and the MOSFETs, and the mounting holes is nothing but just to mount the BMS. Okay, so this is the memory flash which is used on the CPU, and here are the crystal oscillators and some debug programming connectors, and here are the CAN LIN or CAN and LIN transceivers. Okay, and this is the automotive connectors, the main connectors same like this here, and this is also the CAN transceiver, and this is the ESD protections components, and some microcontrollers are also used in this BMS, and these are the voltage regulators just to maintain the voltage level inside the cells, or to maintain the uh, charging level or the state of health in the battery pack. Okay, so like high voltage contactors, we can easily identify by the orange color you can see here, right? So this is like how the BMS looks like. Okay, so that's it. So like I hope you have learned, maybe those who don't know about the system, how this CAN system works here. Okay, so basically this all this system like how a automotive ECU is built by like combining all the MCUs, or like communication between the CAN LIN transceiver or the power management regulators. Okay, so all these like they are the larger board act like a central controller where the all the smaller board operates or as a distributed node. Okay, which enables like a modular or efficient vehicle electronic structure. So this is all about the CAN bus system and LIN bus system, and the BMS, how it is giving messages or signals to the all the systems which are placed inside the vehicle. Okay, so anyone have any questions or any doubt? Anyone have any questions and any doubts? Is Shivani there, sir? Raju, sir? Hello.
Yes,
Am I
just wait a second. Yeah.
okay? Wait, there is a.
If anyone
yeah.
have any question, you can ask, and I'll just take like only few minutes, and after that, I'm going to share you the attendance sheet so you can fill, and just
Yes, yes.
fill those sheet carefully. So, because your certificate will be prepared according to that only. Okay.
You all will get the certificate. Okay, and we have one announcement that Shivani will explain it to you. Okay.
Hello everyone.
Yes, Shivani, you are audible. You can explain all these things.
Okay, everyone, hello everyone. I hope you all are doing great. So I think you all must be knowing about AICTE, which is All India Council for Technical Education. Okay, that approves technical program in India. So basically, we have our online portal, which is called AICTE NEAT portal. Okay, where learners who are interested in EV technology can enroll. Okay, and this is our master certification in EV technology, which is industrially designed with hands-on practice on softwares. The software that you will be getting familiar would be MATLAB, Cassia, Simulink, ANSYS, and much more. Okay, and this is going to be our 6-month online internship program where you will be having 6 different type of modules. Okay, you can choose any of the module or either one, two, or either all of them as well. Okay, and after the completion of the module, you will be given a project as well. And that project will be hands-on training in your near EV labs. Okay. And after the completion of the project, uh, based on your project performance, you will be given placement assessment as well. Okay. And so this project matters the most in this. If any one of you interested in this AICTE NEET courses, you can just enroll in the registered form given. Okay.
Thank you, Shivani. Thank you so much. Everyone, you can mention like 2 to 3 links. One, like whatever the experience you have during this complete webinar, you can write your experience through that Google review form. Okay, and even if we wanted to know like that, what next topic you wanted to learn. See what we usually do, what we currently seeing, like what the things are in industry is going on. According to that, we used to plan this seminar. But if you guys are interested to learn any particular topic, you can suggest so the next webinar will be planned according to that. And I request you all, you can even also invite your friends like in next webinar. We'll provide the certificates. You can post these certificates on LinkedIn, tagging ISA India. And if anyone coming from like our event like Formula and IKEA and ESBC and e-bike, you can tag those pages. So this will enhance your profile on over LinkedIn and make your connection rich. Okay. And apart from this, I have already shared the registration, certificate registration link, where according to this attendance, it will prepare the certificate. So make sure you are mentioning your name correctly, and even if anyone is here who are coming from the industry, you have to mention your organization, and if anyone is, or most of like participants are the students, so you have to mention your name, college name, and if anyone coming from the industry, you have to mention your industry name, like from which organization you are. Okay. And as Shivani mentioned, we are running like certain types of courses, which is already mentioned. Like there are some master degree program that is for 6 months, and there are some summer internship program, and which we are running. So if anyone are interested to enroll in that program, and that is available on very nominal fees. So if anyone is interested in program, you can fill this that form. You will receive a call from our side, and will guide you accordingly. Okay. If anyone have any questions, you can ask. Anyone have any question? You can write in the chat box, or you can unmute yourself and you can ask if anyone have any question. Whoever, like our team participants, like and like anyone who are from the who are not associated with ISA India wanted to ask any questions.
Hello, sir.
Yes, yes.
Hello. Sir, my
Yes,
name is
yes.
Aditya. I want to ask the internship program about
Is it fully online or is it practical also when we can?
So like say it's like total 4 week program. It's hybrid. So there are two types of program we are running. One is completely online, where in that all the classes and everything will be online. And the second one is hybrid. In that 3 weeks and 3.5 weeks will be online. And the last week we have different centers like as Shivani will tell you about that. We have the 4 centers. So according to your comfort zone and according to the what I can say which country you wanted to join. So we have a completely fully fledged EV labs. So you can come there and you will learn about the like suppose recently we have inaugurated lab of GSW Foundation here on Aurangabad, and that is the India's first heavy vehicle of the country. And we have learned you will get the practical insights, and you will 4 week internship. We are not charging like much. That is a very nominal fees. And if you are interested, as I mentioned, you can fill this. Doesn't matter. It's like totally your wish if you wanted to join or not. So from my team, you will receive a call. You can fill your interest form. And most important, if any students are from like second, third, or fourth year and who wanted to submit that particular internship certificate, who wanted to like like everyone used to everyone have to do this internship certificate internship in third year and fourth year, and after that they have to submit a report and a internship certificate. So this certificate will also valid for that in your college if you wanted to submit. Okay, so suppose if we are giving this internship for like 4 week, and if anyone want a certificate more than 4 week, then we'll provide according to the requirement of the students and college. We'll modify and we'll provide that also. Okay, anyone? Any
Thank you, sir.
questions? So who is not like in working in any organization, they have to fill their college name. Okay. So suppose here like many people are from the industry who is working in the industry. So the organization on the organization name, you have to fill your organization name, and who are not from the like the any industry, you have to fill your college name. Okay. So the double is asking about the nominal fees. See, fee you can fill the what you can say the form double. You will receive a call, and you don't worry about it. You will not get a regress call. If you will think you are interested and like the fees is feasible for you, obviously you can enroll for the course. Okay. So I have pasted all these 3 forms. Okay. So one I'm sharing again the attendance sheet. This is the attendance sheet. So fill this for the certificate. Okay. I've said again, this is the attendance sheet. The certificate will be prepared according to this. And one more message I have shared, just a second. This is for the course. If anyone is interested, want to inquire more about like master degree program and the current internship program which is going on, so you can fill this form for the what you can say the internship. And the first one which I have shared, that is related to the review. So however your experience was there during this complete webinar, and if anyone have attended like our previous webinar, okay, so you can write your review on this Google form. Okay, so we can enhance our like quality in terms of trainer, in terms of engagement, and if you wanted to learn any other topic, you can let us know right here. So accordingly we can plan our next webinar. Anyone have any doubt? You can ask. Everyone clear? Anyone have any doubt? I'll just request everyone, please write your review. That is very important for us to improve ourselves. Okay, that is very important. Whatever you feel, you can write your review through that Google form, through that Google review. Okay. Clear, everyone?
Okay, sir.
Okay. So who are like there from the teams like from IKR or Formula? And I hope I know this topic was a bit different from in terms of like formula and IKR participation. And but this is very important. This is the most important topic which is currently going across the industry, and this is the most you can say the important topic for students who wanted to work in fields of AutoSAR and ADAS, and so this is the most important because without understanding this communication protocol, you are not able to work on this ADAS and this AutoSAR and autonomous vehicle. So I know this topic was a bit different from other topic which we have organized earlier. So, but this was very important. So I hope you guys enjoyed that, right?
Yes, sir.
Yes, sir.
So if anyone see, so this was like say in this 2 hours, and whatever webinar we used to conduct in this particular 2 to 3 hours, we are not able to cover this complete topic. Even if we speak about this CAN protocol on a single protocol, it takes like more than 5 to 6 hours to explain. Okay, so if anyone want to learn about any topic like about the EV and about this CAN protocol and CAN communication, so in master degree program we have covered all these topics. Okay, so even like some of like our working professionals are already attending this program and wanted to switch their career and like any other industry, and they wanted to enhance their profile and the knowledge, so they used to attend. See, these are not like the any promotional thing which I'm doing. Okay, so there's nothing to force. So if anyone is interested, want to know, and who is associated with ISA India, they know what we do. So obviously they can inquire and they can get enrolled. Okay. And we usually conduct such types of webinar. You guys know there is no such fees for such webinar. And maybe next week there will be some topic will be related to a student, especially who are waiting to get the insights regarding the events of IKR Formula ESBC. So we are planning to conduct a session from related to GC or some what I can say the bike, the go-kart and Formula, and it will be conducted through like we are looking for the speakers, so maybe it might be from BOS or ANSYS. So I hope you guys will participate like in next webinar with good number from your team. Okay, anyone have any doubt?
No, sir. No, sir.
Okay. Please do fill all the forms. So students who are interested for the internships, you can fill the form. Please write your Google review, and obviously most important, you have to write your fill this attendance form for the what you can say for this certificate. Thank you everyone. You guys can leave. Thank you.